Good afternoon, ladies and gentlemen. Welcome to the Technical Forum. Welcome to the group exhibit, Hydrogen Fuel Cells and Batteries. I'd also like to say hello, good afternoon, good morning, or good evening to our guests all over the world. We are live streaming here. We have an online stream. We stream from the fair. We're in the year of 2015 here at the Hanover Fairground. I'd like to welcome here on stage. He is already here. Peter Wagner, R&D Manager at Next Energy, and he will talk about the introduction into the European project CISTEM. And please explain to us, what is CISTEM?
Okay, thank you very much for having the opportunity to look into our European project CISTEM. And it's an acronym, of course, but it is directly related to the standard word system, which means we are looking at a CHP system that is using high temperature PEM technology, and I will go into details what we're going to do within this project. I'm sorry. Just a brief outline. I will just explain where I'm coming from in just one slide. Then I will explain the goals and the objectives of the overall project. I will show the partners, the structure, and some ideas. And then I will go into the technical goals and, of course, show what we have achieved so far. We are now currently at midterm, that is one half of the project has passed, and I will give a few results that have been achieved so far. And I will close my presentation with a short summary and what is coming up in the next period. Sorry. As I already mentioned, I am from the Research Center Next Energy, and this is our fuel cells division. As you can see, we have 3 research topics. That is micro CHP systems, where it's the engineering side, where we look into testing of complete units. The second one is characterization. That's what I'm heading. We are looking into analytics and, of course, do a lot of single cell investigation, with the main question how a fuel cell degrades. And the material side goes down to the basics and try to develop new materials, mainly in the alkaline fuel cell. The project started in 2013 and is for 3 years. The grant agreement, as you can see, the budget is around 6 million euros, dividing between these partners from industry, Danish Power Systems, Eisenhut, ICI, and I missed one. And of course, the other partners coming from research organizations like ourselves, OWI, University of Chemical Technology, Prague is involved, and UCLM, University of Castilla-La Mancha. Of course, every European project needs to have a vision. Our vision is quite clear. We would like to prove that high temperature PEM fuel cell technology is ready for larger CHP systems. And larger CHP systems we have to find to be up to 100 kilowatt power. And with this, we have a pyramid of development, what we call, starting, of course, at the lowest level on the material side, on bipolar plates, MEAs, coming one step forward to the stacks, bringing together everything into the balance of plant. At the end, we would like to have a complete CHP system with a power of 100 kilowatt. Within this project, we follow a modular approach. Modular approach means we will not have one large stack providing all the power, but we will have modules consisting of 2 times 4 kilowatt stacks plus one small reformer operating with this stack, and then we call this a module, and then we number up the modules to achieve the power that is needed. That was a strong request from the company ICI. ICI is selling CHP units in the power range between 30 and 100 kilowatts and can now very easily adapt the customer demand just by taking some modules for 30 kilowatt or 40 or 70, whatever the customer is asking for. Of course, there are other targets that have become, which is the electrical efficiency should be larger than 40%. And the last approach that we manage is that we want to be fuel flexible. Fuel flexible means we would like to use, of course, reformat hydrogen using natural gas. That is the standard procedure. But we will also switch quite easily to pure hydrogen coming from an electrolyzer system. And the CHP unit will be flexible and can be switched between both of these different kind of fuels. And of course, this requires certain operational points that we have to look into and discuss. First of all, a short explanation about the efficiency strategies we are approaching. We have mainly two approaches. One is to use the oxygen from electrolyzers, not only the hydrogen. The oxygen can also be used, not in the amount that is available, but I will come to this. And the second, which is quite technological, is to increase the back pressure. Unfortunately, this one has to be cancelled because we have to follow the EU regulations, and if we power up a system like this, it is at the moment not clear, and it is just under investigation of it. The CHP unit has to follow a certain EU regulation, and then we have to cancel this. Nevertheless, we can do this, and we can look into the effect of oxygen enrichment. And you can see this with two different types of MEA under the same conditions. And we started with normal air and increased the oxygen content to 30% oxygen to 75, and of course the final one is pure oxygen. That is nothing new. Everyone knows the more oxygen we have, the less mass transport limitation we have in the system, so the efficiency will be better. What is not understood and was not clear when we started this project is how an MEA or a stack will degrade if we introduce higher oxygen content, and that has been investigated. And we did this under synthetic reformate, which means we use nitrogen and hydrogen and nothing else, so no carbon monoxide, which would come back later if we use real reformate. And then we performed a long-term test using load cycling between 0.3 and, in this case, OCV. 16 minutes at 0.3 amps, 4 minutes at OCV, and this for more than 1,000 hours. And you can see the degradation rates. You see different levels of degradation rates. That's why we introduced different losses here. Between the first days, we have a larger degradation rate, and after 10 to 14 days, the system seems to adapt to a much less degradation rate. Of course, it can be discussed if a degradation rate like this is suitable for a CHP system, but you will see later that we are already one step further. First of all, we wanted to learn what is happening with the MEA and the stack under these conditions. We have more chances to improve the efficiency. This is one, using the oxygen. Another is that we use the heat recovery from the fuel processor in a much more efficient way. This has been established, so we are at this point of time at an efficiency above 40%. That was the target. And if we would go one step further and completely redesign your fuel processor, we would be able to achieve more than 43%. But the point here is the fuel processor is designed with standard off-the-shelf components, so it will be very cheap. A complete new design would require new materials, new development, and the fuel processor would be much too expensive to include into the system. And the last approach, which has already been shown in another project, Eureka, is that we need to adjust the operational strategies. And the colleagues managed to achieve about 8% efficiency increase in the best case. In the worst case, they achieved 2%. So I said we would be around 3%. So last not least, I hope that we can manage to achieve 44% of efficiency for our system, which is already quite high. This is another approach. I already told you we would like to use oxygen, and we would like to switch back to reformate from natural gas. And we did this for about 2,500 hours. Just switching every 12 hours between the fuels. And then you can see, of course, we have a degradation rate, which is much lower now. It's about 16.6 microvolt per hour, which is still a little bit too high if we consider the EU targets of 40,000 hours of lifetime. But we managed to get even better. A CHP unit consists of several components. The balance of plant design, of course, is important. So we had to develop the new fuel processor with a certain production rate. That is quite easy, but it is important to have the fuel processor being able to be modulated between 25% and 100%. Why 25%? We have two stacks. If we want to take one out of operation during summertime when the heat is not used, we can use and operate the second stack with about 50% level. And that's why we come down with the fuel processor to 25%. The carbon monoxide concentration has to be around 1%. HTPEM technology can stand a little bit more. 2% wouldn't be a problem, but it is manageable. And this is the fuel processor under investigation in the moment. We see different components, the water gas shift, high temperature, low temperature gas shift that is needed to achieve the low carbon monoxide level, and we have introduced additional heat exchangers to be more effective. On the other hand, we started to use large area MEAs. The area size of the MEAs is 200 square centimeters, and assembled the first short stack and investigated it in a system. And you can see here that we have a quite high degradation rate. This is, of course, not acceptable. We wouldn't be able to achieve 10,000 hours operation. We will want to achieve 20,000, so we had to work on it. But this was our starting point. Now we are in a situation, we assembled the second stack, we improved the MEA. It was a slight improvement in MEA design. It was also an improvement that the ionomer was differently distributed in the MEA, and we used new material for the bipolar plates. And then we assembled the stack once again. And this is quite new. This result is from last week, so it's really a new one. And we achieved with the stack a degradation rate of 5.4 microvolt per hour. And if we take about 20% of energy efficiency loss as the end of life definition, this would be more than 20,000 hours of operation, which is quite good. And that's exactly the target where we want to go. Our final target will be a little bit less. We would like to reach 4 microvolt per hour, but that will be hopefully come with the third generation and fourth generation of stacks, which will be part of project period number 2. Just to give an impression, the CHP unit will be tested in a test bench situation, hardware in the loop design. Hardware in the loop means we will assemble 2 stacks and 1 reformer, so 1 module, and all the other modules will be emulated with a computer program. And this is the standard setup you use if you want to operate a CSP system with the storage tank, reflows, etc. And this we will investigate certain questions of CHP operation in northern Germany in comparison to southern Germany and to central Germany, which of course is regional aspects and of course also the weather conditions that have to be considered. And the second point is the CHP unit will be able to be used in large housing or small housing distributed. That is another situation. Or we can use a large building where power of about 100 kilowatts can be used. So this will also be investigated. And I told you that it is a modular approach. Every CHP system has the problem that in summertime the heat is not needed. So either it is wasted or we have to find other strategies. And one strategy is currently under investigation, that is from the colleagues taking modules out of operation on a regular basis. And if you consider a revolver where you just turn and use the next one, what we have to make sure is each stack, each module has to have about the same time of operation before we can investigate the overall system. And that comes down to a first in, first out operation time. So, to conclude quite easily, what have we achieved? We have improved materials. I mentioned new bipolar plates. It is still in progress, but I haven't shown any data on the material improvement on this side. What we have investigated is the cathode oil enrichment, which is very important. We have investigated different strategies, and the fuel processor design has been finished. First stack has already been operated, and we are currently working on the hardware and the loop testing. What we have to do now is we have to bring everything together and assemble the full stacks to achieve the 4 kilowatt power per stack. And another important aspect is we have to look at the economic aspects of the system. The system needs to be marketable. It should be possible that the price, we have to look into the prices and the development and things like this and see how the market is reacting to this. And with this, I would like to conclude. And of course, I would like to mention that the project is being funded by the joint undertaking. And if there are any questions, I'm happy to answer. And if you want more information, you can come to our booth at D55 and we can go into much more detail. And I will explain if it is of interest. Thank you very much.
Thank you also from my side. Thank you very much for this interesting presentation.
Thank you.
Are there any questions right now from the audience at this time?
No.
Everyone is too shy here.
I know.
You can take your questions to the booth at D55 with Next Energy. Thank you very much, Mr.
Thank you.
Wagner.
Thank you.
Next talk in only 2 minutes' time will be our last talk for the night. It will be the status and prospects of Serenergy sodium batteries. That will be only in 1 minute.